strongly connected components and how to determine the DAG of strongly connected components, correct? Right? So firstly, if we knew a vertex in a sync strongly SCC, then we would be able to find all vertices in the SCC, in the sync SCC. Why is that? Because you would just do reachability from that vertex V. So you would just find the reachable set of V is equal to a set of vertices enumerated in DFS, or for that matter, BFS from V. Correct? And this would exactly constitute this strongly connected component, because all vertices would be reachable from V and no other vertices would be reachable because it's a sync component. So what does a sync component look like? You have one strongly connected component, another one, and yet another one, and maybe yet another one, and through this you have this strongly connected. So this is a sync component. All the vertices here cannot reach anything but what is inside it by following edges of the graph, correct? So if you knew a vertex here, you can just do reach. Okay. So having determined this, if you could determine such a vertex V, you would find the reachable all of, and then you would recurse on the remaining graph. And we'll show how to do that efficiently. But if we can do that efficiently, then you would again find a sync component, and in that sync component, now you would mark all the vertices reachable vertex and so on. So so now how do we find such a sync component? So first, let me say something about source components. So what is a source component? How do you find a vertex in a source component? Is easy. Why? Because everything is reachable from everything. So there is nothing going which enters a source component. Correct? This is not allowed in a source component. Correct? So whether you from within the source component or from outside the source component doing DFS, you would end up at a vertex. The exit source component would be maximum. So let me put it in words. So what I'm saying is the component, the vertex with the maximum exit value lies in a source component. Why is this? Because you will either start the DFS from within the source component, in which case you would traverse the entire graph, and only then you would come back to this. So while going down, you would not get blocked. So think of a DFS. You would.
Do we run the DFS on the entire graph?
Huh?
Do we run the DFS on the entire graph?
Yes, you run the DFS on the entire graph.
Okay.
Starting from an arbitrary vertex. The vertex with the largest exit value is a source component. Because either you start from that source component and you will not come back to it until you have explored everything that is reachable from there. So this, so the vertex visited last would be in this source component, or in maybe in some other source component, but the last visited vertex cannot have an incoming edge. Suppose this component is visited last. The exit value of vertex V belonging to this component is last, and there is an edge coming into it. Whether you start your DFS from something above or something below, you would visit something, the exit value of some vertex here would be more than the exit value of V, correct? Do you agree? Because if there is an edge into a component, so let's call this component C, let's call this C prime. If there is an edge C prime comma C into a component C, then C prime would have a vertex of exit value more than all vertices, than exit value of all vertices in C. Correct? Tell me.
So what exactly is exit value? Is it like a number of vertices?
So exit value. So remember in the DFS subroutine, we had pre-process and post-process. In pre-process, we gave so in both of them we let me go back one lecture. This must have been in the last lecture, correct? No. Was it in the last lecture? No, it was in the lecture previous to that. Sorry. So no, sorry. So where did it go? DFS, sorry. Many lectures ago. So we said this DFS Explorer has this pre-visit and post-visit, correct? Do you remember now?
Yes,
pre-visit said entry and exit.
Yes, sir.
These are the two values that we these are the two values we add to our we mark every vertex with an entry value and an exit value, and a value is the exit value is the time at which the vertex is seen for the last time. After backtracking, it will never be seen again, correct? You have basically explored everything below it, and then you backtrack from beyond it, correct?
Yes, sir.
Yeah. So, so
can you explain that how that works again?
Okay. So you are in a graph. You are doing a DFS. So in DFS, you visit a vertex. Then you so Basically, you are going forward, till you get stuck at a point. Correct? So think of this graph, this directed graph, correct? This is a source component in which there are no incoming edges. This is a sink component, there are no incoming edges. Start from here, you'll visit some neighbor of it. For a while you are inside this component, then you go to another component. For a while you are inside this, then you go to a component, and so on till you reach the sink component. Now you will have to visit all the components, and then you cannot go forward. Correct? So you will backtrack along the path you came and go to this component. If this has another this thing, then you will go along it to that component, visit it, come back, go here. This is already visited, come back here, and so on. So in this way, you backtrack, and once you have completed visiting this component, only then you would go outside it. Meaning you would jump to another DFS component, another component which is not reachable from this component, from this source component. Correct? Are you with me?
Yes, sir.
Suppose this is the graph, you would jump from here to here. You visited all the components below. So you visited this, partially visited this, then you visited this, then you visited this, then you visited this. So these are all partial visits. Then you completely visit this, go back, go to another component, partially visit, go back. You come back, completely visit this, come back, still partially visit this. Then you go here, this is visited, you come back, and so on. So the DFS is clear, correct? Not clear, is it?
Yes, sir, it's clear.
Sorry?
It's clear, sir.
Okay, so now, okay, very good. So exit of V is the, so the component with the largest exit of V must be a sink component. That must be a source component, correct? That's the point I'm trying to make. So the last component, visited source component would have the largest exit number, correct?
Sir.
Tell me.
So what's our aim? Like, what are we trying to do with this whole thing?
So what we are trying to do is to split up this graph into strongly connected components and compute a DAG out of them, correct?
Okay.
So we are trying to compute the DAG of strongly connected components from this thing, correct?
Yes, no, but I don't like. Okay, so right now we have C dash and C, and we are looking at pre-visit and post-visit things. How is this connected to splitting it up? I'm not able to see the bigger picture.
So you want to determine these strongly connected components. How will you find these strongly connected components? You're given the graph.
Yeah, so we look at everything that's connected to one point and like you split it up that way, is it?
No. So here I'm trying to. So what I'm saying is, if I give you a vertex in V, vertex V in the sink component, you can tell me this component, correct?
Yeah.
Because you will just visit the entire thing. Whatever you can from V will be this strongly connected component. But if I give you a vertex here, how will you find this thing? Then you might end up visiting this. Correct? So take this example. I give you a vertex here, you visit all of this, come back, visit all of this. Now there is no easy way to distinguish between where this component ends and where this began. Correct?
Right.
But on the other hand, if magically somebody gave you a V here, you would visit this entirely and mark all these vertices. Now you go back and visit these entirely. So whenever you see a visited vertex, you don't go there. You visited these entirely, and now you know this strongly connected component.
So, if you're given a vertex V, how would we go about visiting every vertex in that click?
You would just in that component, you would just do DFS from that vertex V. You would do DFS or any reachability like BFS or DFS from that vertex. That would give you that component. Do you see my point?
I mean, kind of, but not completely.
No, what is not clear? Tell me. So you are at a vertex V. You want to know
I
which are the
understand. I understand we'll be able to reach all the vertex in the component, but since it's a strongly connected component, it works both ways, right? So vertex A can go to vertex B, and vertex B can go to vertex A. I mean, there's a path
that's
both ways.
that's true.
So how
Yes.
do we like verify that also using DFS or DFS?
So that's a good point. My point is, under the promise that V belongs to a sync strongly connected component, it is easy to find the strongly connected component.
Yeah, that's right.
That's right. No?
Yeah, that I agree with. Yeah.
So now you have to find a vertex. So a vertex in a strongly connected component. In some strongly connected component, so if I give you a graph and you could supply me one vertex in a strongly connected component, I claim I can always be done, because I would find such a vertex, traverse that entire component, and then subtract it from the rest of the graph. I would remove all these vertices. How would I remove all these vertices? I would mark all these vertices and repeat. So there are more ways of doing. We'll see that in minutes. But conceptually, this is what we are doing. We would find R of V, reachable set of V, correct? And look at G and find a V. So it's called this V1. We would find a vertex V2 component of G minus reach V1, correct? Do you see the plan? And then we would look at G minus reach V1 union reach V2 and find a V3 here, which is in a sync component, in sync of this, correct? And so on.
Yes, sir. Yes, I understand this.
Okay. Now, instead of finding sync components, we can find source components easily. So I don't know how to find sync components right now, but I can find the source component easily. And what is a source component? I start from a vertex, any vertex, and take the vertex with the last exit value. Okay. I claim that is a source component. Correct? Do you believe this?
Okay, could you repeat what you said?
I'm saying you start from a vertex R, any vertex R in the graph, do DFS over the entire graph, okay? And then look at the vertex with the largest exit value. The vertex we see the last time in the DFS, after which we cannot backtrack further. Correct? I claim this vertex is in a source component, because had it not been in a source component, I would either it would have been possible for me to backtrack further or start some part of the DF, some vertices would be completely untouched and I would do DFS starting from there, correct? Meaning, I'm just saying if I...
So could you give, like, maybe explain it with an example?
Sure. So suppose I start my DFS here, correct? So there are three components, C1, C2, and C3. C3 is a sync component. C1 and C2 are source components, correct? I start my DFS from C1. I visit C1, go to C3, and so the exit. So, and then what would happen? I will finish traversing both of these. Then I would go to C2. I cannot enter C3 because it's completely visited. And now the exit, largest exit value would be here. Max exit would be here, correct? So C2 would be a sync component, a source component, correct? On the other hand, if you start from, let's say here, you start your DFS from here, you would visit this completely. Then you would try to visit this and do DFS here. You cannot enter here because it's visited. So this has some exit value. Then you would visit this maybe. And then this would again be the largest. Or maybe the exit would be here. In any case, the exit would only be in a source component. Are you with me?
Yeah, yeah.
Okay. So you cannot, okay. So that said, now how do I use this to find a sync component? And this is a very simple observation that sync of G is a source of G reverse. You reverse all the arrows, then while the strongly connected components remain the same, because if you can reach from A to B via straight edges, then you can reach from and B to A via straight edges. Then by reversing all the edges, you would get this here and this here, correct? So the strongly connected components remain the same, but sources and sinks are inverted. Do you agree? Basically, you get the reverse of the DAG in the second case. Are you with me?
Yes, sir.
Okay. So now we know how to form the. So we know how to find sources, and we needed sinks, so we can get sinks from the sources of G reverse. So the algorithm is clear. Do DFS on G reverse. Find, consider the vertices in decreasing order of DFS G reverse, exit DFS G reverse. Let me just write exit of exit on exit values on G reverse, correct? And consider the vertices V in this thing, do D and mark, and in the process mark all the vertices reachable from V. So DFS V will mark all the vertices reachable from V. So I think I used the so I will mark this with DFS V comma V. So remember DFS V comma R marks all vertices reachable from V for the first time with R, correct? So in this example, you would, if you start from here, you would, no, actually this is not correct, but no, this is correct. This is correct. Sorry. So this is correct. So first you would do consider the vertices V in decreasing order from in exit in G reverse. So in G reverse, what would be? So you would discover a thing in a vertex in the sync component of G, some vertex V here.
And then you would do DFS from here. So you would discover all these vertices and mark them with V. Then you would take one vertex which has a lesser number, say this or this, and then you would do DFS here and mark it with that vertex V prime, V1. So maybe this V3, and then you would mark it with V2. Correct? Am I making sense?
So do we remove C3?
Do we remove?
C3 before starting?
Yes.
Yeah.
So we remove C3 by marking the vertices with V3.
Okay, so
Next round, we would just consider labeled vertices, unlabeled vertices. Sorry, what am I saying? So we would only consider unlabeled vertices, unmarked vertices, correct? So
okay,
we
sir.
will mark all vertices of C3 with V3. And then we would, in the next round, in the next iteration, find a V which is a V1 or V2. And suppose we find V2, we would mark all the vertices here with V2, correct? And all the vertices here with V1 and so on, correct? So that would.
Sir,
Tell me.
I don't understand the last step where you've written DFS VV. What does that mean?
So DFS VV I explain here. I will mark, while doing DFS, we will mark the vertices reachable from V by the label R.
Okay. Oh, so as in to identify the component of V, is it?
Just to identify the component.
Oh.
Everything with the same label gets identified with that component.
Okay, sir.
In one component, falls in one component.
If we
So
want to find a sink,
sorry?
so if we want to find a sink,
Huh?
why can't we just do one DFS and keep going until we reach some vertex that can't go any further?
Yes, that's true. You find a sink, yes.
So isn't that easier than reversing the tree?
You can do it with one DFS also, but the algorithm would be more complicated because then you would, when you find a sink, you would have to so you would have to go back and mark the vertices with that sink, correct?
DFS needn't stop at sync, right? Like if it can't go further, it will stop, right? If all the neighbors are marked already, it needn't be a sync, right?
Oh, you are saying that if we do it on G, then would we find a sink? So you are absolutely correct. The second person that just said, you will not be able to find a sink this way. You cannot find a sink doing DFS and then when you backtrack, it's not necessarily a sink. For example, let's take this example. Just a graph. You have this and this and this and this. Correct? Let's say. No, sorry. So tell me what was this thing? What was the objection? What was the alternative thing that you proposed? The person who proposed?
I mean, the proposal was that we just start with any vertex and you do a single DFS until you reach some vertex which doesn't have any way to go.
And then you backtrack beyond it.
So why do you have to backtrack? I mean, we'll reach a sync vertex at the end, right? Because it can't loop back on itself because it's a tag, I think.
Yes, but then how do you proceed after that? Suppose you found a sync vertex, then you abandon the DFS and then you again do. Then what will you do?
So once we have one sync vertex, we can find all the sync vertices, right?
No, how?
Because it will be they'll all be in the same component.
No, why?
Oh, if you want to find all the sync vertices, all the syncs.
And moreover, something might become a sync after you remove some parts of the thing. So, yeah. So you would have to find the syncs here. You have to find the syncs here. And then when you have removed all of them, then this would become a sync and you would have to find a vertex here and so on, correct? So here we do one complete DFS on the reverse. And reversing is not hard. You can reverse all the edges. You can reverse all the edges easily. I leave that as an exercise, but it's very easy. I mean, in degree, out degree, like we saw in the, yeah, so I will leave you to argue about that. But you just have to do one complete DFS and then another DFS. So it's twice the usual DFS time, but that's okay. It's asymptotically the same. Correct?
Sir?
So I would advise you to read this section from Dasgupta. And Wazirani. Their book on algorithms has a good exposition of this algorithm.
So,
okay. Tell me.
So no, I don't like what was wrong with the suggestion? Like what?
See, so you can find one. He's correct that you can find one sync vertex, but then you have to erase the and okay, you find one sync vertex, you erase the you mark all the vertices reachable from that sync vertex. Now, how do you find another sync vertex?
So can't you go back to its like parent component and then go from there?
So yes, that is a good suggestion. So you can pause the DF point of correct, and do another DFS in this part of the graph, complete this, and then go back to the previous one, continue the DFS there, and so on. So it is possible to do it with that one DFS, but asymptotically the time taken would be similar. And this is conceptually neater. Do you agree? Because again, you would, yeah, so you would interrupt your original DFS when you find a sync vertex, and then mark everything reachable here in one shot. Then you revert back to the original thing and you go back and then you find another sync and so on, correct?
Yes, sir.
Okay. So this is, you can read the chapter on strongly connected components. Strong connectivity or whatever.
Sir, just a question. Our original, so by finding a sync vertex in what we were just talking about, do we mean a vertex in a sync component?
A vertex in a sync component, yes.
Okay, so I'm not convinced that DFS needs to even find such a vertex, because it could.
I was also not
be
convinced,
stuck
but
up.
then I found a counter example. So can you give me a counter example?
I think so, sir. Sir, if we have a root, let's say. Oh no, sorry. No, I'll need to think about this.
Yeah,
I'll see
yeah.
it.
So I also want to think about it offline. I was trying to construct that above, but I could not. And I think I'm not sure whether it exists. So I think about it, but yeah.
Okay, sir.
Okay. Yeah, this might not be a sync component. For example, you might this, and you might come here. You find no, but you have this. No, I think it is. Yeah. I think. So anyway, so now we move on to a new topic. Okay, and this is an advanced topic. So henceforth, all the topics would be different from each other. The core topics are finished. We will take bits and pieces from here and there and give you some feeling about data structures, probabilistic algorithms, and so on. Correct? So now today what we are going to start out, and I will just be able to start it, is something called binomial heaps. Okay. So what are binomial heaps? So firstly, I have not told you what a heap is, correct? A min heap. And I will not tell you how to implement a min heap, though I will tell you what a min heap is. Okay. So a min heap is a data structure in which you can find the minimum element. So you can find minimum element, delete minimum element, and of course you can insert an element. I should have listed this earlier, and create a heap. Okay, so here implicitly we have assumed suppose you are given integers or any numbers which can be compared, any objects which can be compared, correct? Suppose you have a set S and an inequality on them, so that you can say S1 is less than S2, and you want to find, so this is a partial order, or this is a total order. Let's say this is a total order on this thing. So for all S1, S2, you can say whether S1 is less than equal to S2 or S2 is less than equal to S1. So suppose you have a set with the total order, correct? And you want to be able to create a heap of objects from this set, such that you can insert an element, find the minimum element among the sets you have inserted, and delete the minimum element from the sets you have inserted, correct? So those are the operations we want to support, and a min heap usually does this, does all of this, maybe this in order 1 time, but these in order log n time, correct? Maybe this even in order 1 time, whatever, correct? So these two in order log n time, delete minimum element and insert an element in order log n time, and it creates a heap and finds a minimum element in order 1 time, correct? Are you with me? So this is an empty heap. Correct? Now in binomial heaps, we are going to give a particular implementation of many heaps, which allows you to merge two heaps also. Correct? So you have the following operations on binomial heaps. First thing is make heap, which creates a new heap, which is in order one time as before. Find min, this is also in order one time like before. Insert is also order one time. And delete min is order log n time, like here. And finally, you can meld two heaps in either order time, or we will see another implementation in which you can do in order one time. This. So this is via eager heaps, and this is via lazy heaps. Lazy binomial heaps, and yeah, correct. So advantage over heaps is that this inserting an element has gone down to order one time. Correct? Are you with me? Firstly,
Yes, sir.
secondly, next time we are going to see further changes to this binomial heap. Next time or the time after that, we will see Fibonacci heaps. Fibonacci heaps. And there you can do an arbitrary delete in order log n time. And you can do decrement, which basically changes, reduces the value, the key associated with an object. This
Sir,
also
what is the last function that you wrote in binomial heaps?
meld.
Okay.
Correct? So this merges two heaps. So if I give you two heaps, it merges them in either in order log n time or in order one time. And when I say order one time, this is not order one worst case time, but so these are all amortized times. By that I mean, if you take the average over a run of inserts and of these operations, on an average, they would take the given times. A single operation might take a lot of time, but overall, if you run many such operations, the total time taken would be whatever I have written. For example, if you do k delete mins, it would take k log n time. And if you do make heaps, find mins, inserts, some number of them, then many of those, it would take plus k prime time. Right? So if you do k prime many such operations and k many these or these operations in the eager heap case, then you would take k plus k prime. Are you with me?
Yes, sir.
Okay, so how do we go about doing this, and why should we care about this? So I will not tell you why you should care about this. This you will learn in algorithms. But for those who know about Dijkstra, this helps in Dijkstra. So the complexity of Dijkstra with min heaps is order m plus n log n time. And with Fibonacci heaps, it becomes order m plus n log n time. Correct? So basically, the crucial point is this decrement. This, if you can do in order 1 amortized time, you get this running time. And if decrement you implement as delete and insert, there should also be, let's say, decrement here. And these are all, login time.
Sir?
Tell me.
No, what are the time complexities you've written? Like, order m plus n log n for which operation?
So m is the number of edges, and n is the number of vertices. So this is for Dijkstra, which I have not covered deliberately. This you will cover in algorithms. Okay, so I will not. Tell me.
Oh, no, sir. I just said okay.
So, roughly speaking, Dijkstra computes the shortest paths, which for unweighted graphs, for weighted graphs. For unweighted graphs, you can do it in BFS using order m plus n time. There is an order log n overhead using heaps. And using Fibonacci heaps, you can reduce this to only log n time for the vertex operations. For the edge operations, it takes order 1 time. Okay. So it's not too much worse than BFS. That's what I'm saying. Okay.
Yes, sir.
Okay. So I still have some time. I have 20 minutes. So let us, correct? So binomial, for binomial heaps, I would have to define binomial trees first. Okay. So what are binomial trees? Let me list some of them. So this is B0. This consists of the single vertex. B1 consists of a vertex with B0 below it. Correct? So you take a vertex and attach B0 below it, you get B1. Now you take a vertex and attach so you take a B1 and attach a B1 below it, then you get a B2. Okay. And now if you take a B2, you take a vertex, on one side you attach a, so this is a, sorry, what am I doing? This is a B3. Basically what we are doing is, we are taking, there are two ways to see it is. One way to see it is, you in a BI, you have all the B0, B1 till BI minus 1 here, correct? Sorry, I did this wrong. So I should have said. Yeah. So recursively, a BI consists of a vertex with B0 through Bi minus 1 below it. Are you with me?
Sir, but where is the extra vertex coming? I mean, in B2, for example, we have two B1, but no extra vertex that is being attached between them, right? In the picture.
No, so this is the top vertex. You have a B0, this is a B0, and this is a B1.
Oh, okay, okay, sir. It's a B0 and B1. Okay.
Here you take B0, B1, and B2.
Okay, okay, sir. Now I understand.
And attach to this. Correct? Correct? This is one way to see it. The other way to see it is you take a BI, so BI minus 1, correct? So BI minus 1 is some this thing. So basically you take two BI minus 1s. So how do I draw it? You take a BI minus 1, which is some graph, correct? Or some tree with one vertex at top, correct? And you take another BI minus 1 and attach it, this way. So attach another BI minus 1 here. So this one is a BI minus 1, and this is another BI minus 1. Correct? Now convince yourself that these two give the same object. This is BI. Are you convinced? That these two are the same. Hi, are you with me?
Yes, sir.
Yes, sir. Yes, sir.
Correct. Why is that so? It's very simple, because till BI minus 2, if you just exclude the last BI minus 1, this would give, so I shouldn't have written BI here. This, by definition, is BI minus 1. Correct? And to which we attach this BI minus 1 here. So this is also BI. Both these additions are equivalent. I will let you convince yourself. Correct? And it's easy to see that BI has, size of BI is equal to 2 to the power I. Because just from this, correct? And the base case. Do you agree?
Yes, sir.
Okay. Now we look at, we say that binomial tree is heap ordered if the value stored in a node is smaller than the values stored at its children. Correct? So you store, so here I should have said first that a binomial tree stores values at every node. Correct? And this binomial tree is heap ordered if the value stored in a node is smaller than the value stored at all the children. Correct? Are you with me?
Yes, sir.
Now, what is a binomial heap? A binomial heap is a binomial heap is a set of binomial trees of different let's not put it there because we would get binomial heap of trees such that along with a min pointer to the minimum valued tree. Minimum value. So to the tree with the minimum value at root. Correct? Are you with me? So for example, if you have, this is a B0 with a single value. So this is a B0 with a value 100. This is a B1 with a value 50 and 60. And this is a B2 or let's say this is a there is no B2, there's no B1, there is a B2 with value 25, 80, this thing, correct? So this is our B2. There is no B1 in here. This is a heap. This is a heap, correct? Containing how many elements? 4 plus 1, 5 elements. Correct? So this is a binomial heap with the min pointer be pointing to this. And moreover, for convenience sake, we will assume the children of every node are arranged in a doubly linked circular list. So basically you have, there's a list from here to here, this is one list, this is another list, and this is another list, correct? Do you see my point?
Okay. So what are the lists here?
So these lists just store the next element in the sibling list. So you have a node, correct? This has many children, correct? All these elements are stored in a doubly linked list, and maybe this. Sorry, I drew it wrong. I mean, it's a doubly linked list, complete circular doubly linked list, correct?
Okay.
So you can traverse from anywhere to anywhere and so on, correct? Now, with this, now let's what is find the rank of an element X is the number of children. Correct? Okay, so in a what is the rank of the root of BI? Rank of root of BI is how much? It's just I. Correct? And so on. So it's just a to denote these BIs. So rank of BI is just basically I, correct? So I'm not said much. Another operation, one operation that is important is linking to binomial trees. So if you have a BI and another BI, you can, this is this, you can make it into BI plus 1 by linking their roots. Do you agree? So this becomes a BI plus 1. And you will ensure that you link it in such a way that the minimum element is here. That the heap property is maintained. It remains heap ordered. The value stored in a row and the value stored at its chain. Correct? So now you will make the tree with the minimum of the 2 pointers as this. So this is linking. Correct? Now comes the fun part. So let me define how to meld two binomial heaps. Correct? So what is one binomial heap? You can represent it like B0, B1, B2, B3, B4. Either there is a binomial heap here or no, and write a binary number like this. Correct? Can you see what this represents? This binomial heap. And basically it has an element called B0. I mean, it does not have any element corresponding to B0. It has a tree corresponding to B1. It has a tree corresponding to B2, no tree corresponding to B3, and one tree corresponding to B4. Correct? This is heap 1. There's a heap 2, which is like, let's say 1, 0, 1, 0, 1. Correct? Now, what is your guess? How will we form the meld of these two?
So can you explain how this works, like the binary thing, and how do we construct heaps, like giving the binary?
No, so suppose your structure is, suppose your data is arranged in 2 heaps, such that, so I will draw one heap. I'll draw from right to left. So it contains a B0. It does not contain a B0, sorry. It contains a B1. So what does a B1 look like? It looks like this, correct? Then it contains a B2, which looks like I'm writing from right to left, but let me draw the heap all the same from left to right, correct? And then it doesn't contain a B3. There's a B3 is missing, and then it contains a B4, which I don't want to draw, but because it's a 16 element tree, correct? So this is what my first heap looks like, correct? And it has a min pointer. Suppose it points to this. Correct? This is what a heap will look like. Correct? Do you agree? Do you agree? Tell me.
Yes, sir. Yes, I understood.
Okay. And the heap 2 will look like something like there would be a B4, there would be a no B3, and then there would be a B2, and there is no, there is a B0. correct? Now I want to merge these two into this thing. So this has 2 to the 4 plus 0 into 2 to the power 3 plus 2 to the power 2 plus 2 to the power 1 plus 0 into 2 to the power 0, many elements, correct? And you do the natural thing, which is to add up these two numbers. So similarly, this is 2 to the power 4 plus 2 to the power 2 plus 2 to the power 0, correct? Now, how would you add up these two numbers? Let me raise this part. And how would you add up these numbers? You just do binary addition, 1, 1. Here you get a carry, so 1. And then this is 1, 1, 0, something like this, correct? And we do exactly the same thing here. This, so some of them, the sum of these two heaps consists of the unique B0 when you add this two. Then you add B1 and B0. So there is one B1 here and there's no B1 here. So you get a B1. And then two B2s. So you will link one B2 and B2 forming a B3, which is the carry. Correct?
So could you repeat the last line? I think you broke up.
So what I'm saying is when you add up two B2s, you get link them and you get a B3.
Okay.
You might say that I took a bad example. Okay. There is a B3 here and here also, correct?
And the B2s are being linked based on which one has the smallest element as it's known, right?
Yes, exactly. The smaller element goes on top and the other root is below. So it remains a ordered tree. And now you get one here. So I changed the example midway. There's a B3 here and there's a B3 here. Now what would you do? So I get a carry of 1 and 2 ones here. So you would write a 1 here, let one of the B3s remain, add the other two into a B4 and carry it here. And now this would become this. So you would get a B3 and then you would carry over this thing, B4 and B4 become a B5. There would be one B4 remaining and the other would become a B5. Do you see what is happening? You're just doing kind of binary operation, binary sum of two binary numbers, and each sum is replaced by a linking. There are at most 3 ones in a, so what are the numbers that you get? Or 1 plus 1 plus 1, this being the carry from the previous one, correct? In this case, there is nothing to do, correct? You will also get maybe 1 plus 0 plus 1, which is the same thing as this. So in this case, there is nothing to do. You just output the same B. Here you put the unique. Here you convert, you don't put a B, and you carry one to the next one. Draw it like this. So there's a carry. And when there are 3 things, then you take any 2 of them, add them, link them, and one of them is. Are you with me?
Yes, sir.
Now, is there any confusion? If anybody is confused about this, tell me.
Sir, how do you arrange the individual elements, sir, in each heap?
So individual elements are arranged. So here I am telling you how to meld 2 things. Now next time we will see how to use this meld to basically do insertions and deletions. Correct? So let me do it in 1 second. So what is insert? insert I comma H. Insert the element I in H is equal to just meld of H with make heap with I. Do you see my point? So you take the unique element I, make a B naught with that, and meld it with the existing heap. And now you can see why I said that this is an eager meld operation. Why this takes order log n time? Because there are just log n many exposed nodes. There are log n many nodes here, which you will, I mean, this is a log n bit. So to deal with these log n bit numbers, you will spend totally 2 log n time, which is order log n. Do you get me? And let's, so insert we have done, meld we have done, rather meld did, insert from that. Find min is just, you know, the min element, and while doing the melding, you can maintain the minimum element amongst the two things, correct? So when you meld the things, you can maintain the insert, maintain the min, correct?
Yes, sir.
And so find min is easy, make heap is trivial, and delete min, how is it done? That we will see next time, correct?
Sir, just confirm. Sorry. I'm just confirming. This is eager, is it? Like all these.
This one is eager. Yes, this one is eager.
Okay.
So delete min, how do we do? Let's do it in very quickly. So if you have, so suppose the min points here, correct? Correct? Somewhere the min will point. Some root will be the minimum, and it will have some children, 3 children in this case. Correct? You just remove these children and meld it, make a heap out of them, and meld it with this. Do you see my point? So this is the minimum thing. Is your H. From H you have removed one child. That took order 1 time. Now you meld the 2 heaps, H and H prime. And that will take order log n time. Are you with me?
Sir, could you repeat what H prime is?
What is?
Sorry? What H prime is?
H prime is the children of the minimum pointer made into a new heap. So suppose your points to some bk. This has k children, correct?
Oh yes, sir.
So you will remove this root of this bk, and you will be left with k many nodes, correct?
Oh yes, sir.
These you form a new heap. H prime put and you can find steps, correct? K is the log n.
Sorry, I couldn't hear in between.
Sorry. So there are these k elements, k elements, which were children of bk.
Oh yes, sir.
You find the minimum amongst them. Say the minimum points to something, correct? This you can do in order k time, which is order log n, which belongs to order log n, correct?
Yes, sir. Yeah.
And now this is your H prime, and now you meld it with the original minus the BK.
Okay, yeah, got it, sir. Thank you.
Correct. So all these operations I just told you how to do in the this thing. The only thing left is this lazy heap. So we will do this and the Fibonacci things next time. Correct.
So I had one doubt, sir. I mean, not related to this, but just a doubt about like how to what extent will we cover heaps and Fibonacci heaps and all this?
So we will do them in detail.
So they'll, I mean, we'll do how we'll construct them in code.
Yes, maybe I'll try to give an assignment to construct to implement Fibonacci heaps also, because as you can see they are not very hard to actually implement. Conceptually they are very simple. Do you agree?
Sir, but to meld to general heaps, like it will be difficult a little.
Why? You just have to do this binary addition, mimic the binary addition, and wherever you see 1 and a 1, 2 ones, you
okay, sir. Yeah.
You get a carry, and then you just take that tree and put it in the next column, and so on.
Okay, sir. Okay.
Just log in length.
So we start with the lowest tree, like the tree with the lowest number of. Okay, sir. I understand.
1 to 0. This gives you 1. Now you get 1, 1. You get 1. Here you have to take care that all the two heaps, the two heap which is carried over to the next one. Now there are 3. So you merge any 2 of them, keep the third one here. Any 2 you can merge and keep the third one here, and that goes to the next one. And then any 2 you merge, that goes to the next one, and this one goes here. Correct? Are you with me?
Yes, sir.
Okay, so we'll continue next time. Okay, thanks.
Sir, one more thing, like Rome is. Sir, can you draw a square? Sir?
Sorry?
Can you draw a square? Like,
can I draw
had
a square?
Yeah, and an edge like sticking out of the square.
Okay.
No, like from an edge, like from a vertex. Yeah, it's a graph, and the square is a like cycle, and
okay,
and the edge is pointing outside. It's a directed graph. And you run DFS from a vertex in this square.
Okay.
So it needn't end at a sink, right? It's a directed graph.
This
yeah, this, cycle, and then it's outside.
Very good point. Very good point. Very good.
Yeah.
Thanks for that counter example. Yes.
Okay.
Thanks. Yeah. So that thing is not correct, but there is a single hop. You can do it with a stack, with multiple stacks and so on. Correct. I mean, so there is a way to do it, but this is conceptually simpler somehow. Okay, so we meet next time.
Is this a counter example too?
This is a counter example to the fact that if you find if you have to back, then you are at a sink component. Back you have to backtrack, only then you can go sink. Correct?
So could you repeat? I think you broke up.
So I think there's some network issues
I'm
on your
saying
end.
you start this. I'm in CMI, so there should not be an issue. I don't know why it's happening, but let me try to complete it. So you start from a root R and you do a DFS. You will reach R if you follow this is one DFS, correct? And then you have to back, and then only you can go here. So you would think that this is a sync component, but it's not a sync component. There is a edge out of it.
So wouldn't the graph have to be a DAG? Or is that not necessary?
Does the graph have to be a DAG? No, it's not a DAG.
So then there could be a graph without any source and sync, right?
No. So no, what is the point you're making? There is no source here. Yeah. There's a source component, there's no source here.
Okay, so I assume it was a DAG. Okay.
Thanks. Okay, bye.
Thank you, sir.
Thank you, sir.
Thank you.